Okay, floating point representation. There's a problem in computer storage with decimal places, because now I've got to figure out how much do I want to store, how much space do I need to create, how many bytes for the whole numbers and how many bytes for the decimal places. So the way they solve this is they only store decimal places, and the point gets moved up and down. So what I mean by that, so I've got two examples of a decimal number before we move on to binary for ease. So let's say we had the number 567.89. So we had the number 56789, and the decimal point is held over here. But now I don't want to have to store what's on the left and what's on the right. I only want to store what's on the right. On the left can just be a sign, which 0 is positive. So we're only going to go through positive numbers for now. All you would do is change it to 1 to be negative. So 0 positive, 1 negative. All my examples here are positive, but literally to change them from positive to negative, you just change 0 to 1. So we're going to move our decimal place here 1, 2, 3 places to the left. So because we moved it 3 to the left, the answer for this one is the exponent is 3, meaning, and the Mantisa is 56789. Now what this means here is that, so it stores 0.56789 times 10 to the minus 3, so 10 to the 3. So representing that, that's 0.56789 times 10 to the power 3 times 10 to the power 3, meaning that to get the number back, you just move to the right 3 places, and that would be the number. So now you don't have to store all of the things there. So now in the next example, so that's the answer to this one here, because remember this is to the base of 10. Now for the next question, random question I've got here, is we have 0. So we have 0, 0, 0, 1, 2, 3, and our decimal placeholder is over here. So in this case, we need to move, so I'll delete my sign while my Mantisa and my exponent. It is a positive number, so sign is 0. The decimal place moves 1, 2. So now it moves 2 to the right, so my exponent is negative 2, and my Mantisa is 1, 2, 3. Easy as that. Now, in this representation, that is 0.123 times 10 to the power negative 2. So now, how do we deal with this in binary? It's the same concept. The only difference is that our exponents are stored and our sign is all stored in binary, which means that my exponent uses what's called 2's complement. So we'll go through that during the process of this as well. Now, my first number is 101001. So let's put that up here. So we have 1, 0, 1, 0, 0, 1. Okay, I'm going to move these all over a bit one because I've managed to get off my screen there. So my decimal point is over after the 1, so it's here. So I need to move that decimal point to the left 1, 2, 3 placeholders. So first of all, it's a positive number, so 0. My exponent is now 3. But it has to be defined how many bits each are used for. So what we defined beforehand is how many bits are used to represent. Now the sign will just be 1 bit. The Mantisa in this case I'm going to say is going to be 8 bits. And the exponents in this case I'm going to say is going to also be, let's do 4 bits for the sake of simplicity. So you would be defined on what it is. So now my exponents I know is it's moved 1, 2, 3. So my exponent is 3, but that's not in binary, is it? That's not binary at all. So I need to try to convert it to binary. So how do I do that? So to convert it to binary, I'm shuffling things around here, sorry. Anyway, to convert it to binary, we need to have, we're using 4 bits of binary, and we're using 2's exponents. So it's 1, 2, 4. Now the biggest number becomes negative. So then to work out the number 3, it would be 0, 0, 1, 1. So using 4 bits, it's 0, 0, 1, 1 is my exponent. And my Mantisa it uses 8 bits. So to come up with the number 101001, using 8 bits, I would need 101001. That's 1, 2, 3, 4, 5, 6, 7, 8. So that would be my exponent there. So the equivalent in 2 bits for this would be 0.10100100 times 2 to the power, because remember it's a base of 2, to the power 0011. I really need to make these things smaller so we can see all of this. I really should have set up the spreadsheet better. Anyway, I hope you guys can see this from there. But anyway, I think this is quite a good representation, despite it being a little bit pear-shaped here and there. Alright, now the next example is the one we're going to go through now, which is going to be going the other direction, because now it's 0.0. So now it's 0, 0, 0, 1, 0, 0, 1, and my decimal placeholder is over here. So now we need to move it to the right. So I'm going to delete this again. We have 1 bit for my sign, 8 bits for my Mantisa, 4 for my exponent. So I'm going to have to move this 1, 2 to the right. So my exponent is negative 2. My Mantisa is 1001, and my sign is 0. So in 0, 1, 0, 0, 1, that's 1, 2, 3, 4, 5, 6, 7, 8. My exponent, I need to come up with my 2's representation again. It goes 1s, 2s, 4s, and my biggest bit is going to be negative. So I'm going to have a negative 8 because it is a negative exponent. So negative 8. And I need to get to the value 2, negative 2. So I need to add 6 to negative 8 to get that. So that's 1, 1. So negative 8 plus 6 is negative 2, 0. So that means my exponent is going to be 4 bits long, which is going to be 1, 1, 1, 0. So to represent that, it will be 0.1001, 1, 2, 3, 4 times 2 to the power 110. Oops, 1110 is my floating point notation. Hope this video has helped you understand a floating point, and a reminder, please check the website du-range.tech for courses and various different activities on that.